Hi there. I'm so glad that you clicked play. Welcome to geometry. This is lesson 1 and 2, points, lines, and planes. Let's get ready to learn. So, this is one of those fancy optical illusions. If you mess around with this with a piece of paper and a pencil, you'll realize that you can't get the pencil to go through the paper like this unless the paper is bent. So, oh yes, sorry, Rex. Oh, you did it, but you did have to bend the paper. Okay. Well, thanks for sharing that. Oh yes, Maribel. No, you're right. It would not be possible with a solid board. But this does illustrate some of the concepts that we're going to use in geometry. This board would be like a plane, and this arrow would be like a line. And there's rules about how lines and planes and points and things like that interact. So here are some things that we can't really define. We just kind of take them as they are. A point indicates a location and has no size. Even though you draw a point, some of your points you draw bigger, it still represents no size. It has no width and no length and no depth. And you can call it a capital letter. You can call this point A. A line is represented by a straight path that extends in two opposite directions without end. It goes on forever in both directions, and it contains infinitely many points. Although we generally will draw like 2 or 3 points, but it's understood that there's infinitely many points all along this line. In between any 2 points, you can draw some more points. You can name a line by 2 points. You can call this line AB or line BA, or you can call it a single lowercase letter like L, line L. That's cursive. That's fancy. A plane is represented by a flat surface that extends without end and has no thickness. A plane contains infinitely many lines. So this is how we draw a plane. This is how we draw a 7 on the plane. And this is how I erase the 7 that I accidentally drew on the plane. So you can name a plane by a capital letter. They usually throw it in the corner of this drawing that represents the plane that goes on infinitely in every direction. Or you can call it by 3 points, like plane A, B, C. Points that lie on the same line are collinear points, and points and lines that lie in the same plane are called coplanar. So these points A, B, and C, we would call those coplanar. But all 3 of them are not collinear because you cannot draw one line through them. So, what are 2 other ways to name line QT? So here's QT. This line sure is a cutie. So what are 2 other ways to name it? So we can name it QN. We can call it line QN. There's 2 points on the line. Or we could call it line TQ. There's 2 other ways to name line QT. What are 2 other ways to name plane P? Well, we learned 2 ways to name a plane. We can use the letter that's hiding in the corner, or we can use 3 non-collinear points to name a plane. So we can call it plane RQV, or we can call it plane, let's pick 3 other letters, QSV. So there's a couple more ways to name plane P. What are the names of 3 collinear points? Well, 3 collinear points, I see 3 collinear points right here, R, Q, and S. So R, Q, and S are collinear. And the next is, what are the names of 4 coplanar points? R, Q, S, and V are all coplanar. So R, Q, S, and V are coplanar because they're all on the same plane. They're all on plane P. We can't say that R, Q, S, V, and T are all coplanar because they're not all on one plane. They're just not. Okay, so pause the video and see if you can figure out these 4 questions. Welcome back. I hope you had a nice pause, and I hope you were able to get some answers here. Let's go ahead and check your work. What are 2 other ways to name line RS? Well, I'll give you a few. We can call it line SR. That's for one. We can call it line RQ. We can call it line QR. We can call it line QS. And we can call it line SQ. And those are all just different names for the same line. Oh, we can call it line L. Alright, it's got the little L there, so we can call it line L. What are 2 more ways we could name plane P? Okay, so we already did RQV and we already did QSV. We could do RSV. Plane RSV, or we can call it plane VQS. Even though we're using the same 3 points that we used up here, they're in a different order, so technically it's a different name. Alright, what are the names of 3 other collinear points? Well, T, Q, and N are collinear. And then what are 2 points that are not coplanar with R, S, and V? So R, S, and V, the only 2 points we have that are not coplanar with R, S, and V are T and N. Those are the only ones that are not on plane P, or at least the only ones in the picture. There's infinitely many points that are not on that plane, but the only 2 in our picture are T and N. Okay, so the terms point, line, and plane are not defined because their definitions would need words that need also to be defined. Like space. Space is the set of all points in 3 dimensions. We can use these terms, point, line, and plane, to define other words. So what are some of those words we can define? How about a segment? A segment is part of a line that consists of 2 endpoints and all the points in between them. So if we have line AB, we can say, hey, let's just consider the points A and B and all the points in between them, and now we call that segment AB. And so the way you write that is just you don't have the arrows on top here. You just have a line segment. So this is segment AB or segment BA. A ray is a part of a line that consists of 1 endpoint and all the points of the line on one side of that endpoint. So if I pick the point A, I can say, all right, well, I'm going to go in this direction, and that's ray AB. You always say the ray, you start with the endpoint, and then you say the point that it's going through. So ray AB always has to start at A and then go through B. If you say ray BA, or let's just say ray BA, this would be ray BA. So it's important what letter goes first. That'll tell you what ray you're talking about. Opposite rays are 2 rays that share the same endpoint. So you can name opposite rays by their shared endpoint. So CA and CB are opposite rays. They share the same endpoint and they form a line. So if you had if you had something like this, ray xz and ray xy would not be opposite rays. Even though they share the same endpoint, they don't form a line. They form an angle. So you have to have both. You have to share the same endpoint and you have to form a line to be opposite rays. So what are the names of the segments in the figure at the right? Well, here is segment DE, and I can also call that segment ED. There's the big one is segment DF, so we got segment DF. We could also name that segment FD. We've got segment EF. We could also name that segment FE. So those are the segments pictured in this picture. Did I say picture too much? Sorry. What are the names of the rays in the figure? All right, so if we start at point D, we don't have another point going in this direction, so we can't name a ray going that way. But we can name it ray DE, and that same ray we can also name ray DF. Then we've got E as an endpoint. Going in this direction, we got ray ED. And then in this direction, we get ray EF. Now these two happen to be opposite rays because they share the endpoint, E, and they make a line. All right, what else we got? If F was an endpoint, we could do ray FE, or we could call it going through D, and that's ray FD. Which of the rays in part B are opposite rays? I already did that. ED and EF are opposite rays because they share the endpoint E, and they form a line. Okay, so why don't you pause the video and see if you can figure this out. So EF, so here's ray, I'll kind of draw a picture of what ray EF kind of looks like. And then ray FE, if we were to separate those two rays, they would look like this. So are they opposite rays? The answer is no. They do form a line, but they don't share an endpoint. And you need both of those conditions satisfied in order to be opposite rays. So a postulate or axiom is an accepted statement of fact. We don't prove them. We just accept that they're true. And we use logical reasoning to prove general concepts. So we've used some of the geometry postulates. Let's go over what some of these postulates are. Through any 2 points, there's exactly one line. So if you have point A and point B, there's only one line that goes through those 2 points. There's not two. Whenever you have the intersection of 2 distinct lines, they intersect at exactly 1 point. We used that in Algebra 1 when we were solving the systems of equations. You remember that, don't you? Well, another thing you should remember is the secret phrase for this lesson, which is vegetable samosa. Vegetable samosa. All right, so here's postulate 1-3. If 2 distinct planes intersect, then they intersect in exactly one line. And here's a picture of what that looks like. 2 planes are intersecting. The place that they intersect at is a line. All right, so finding the intersection of 2 planes. Each surface of this box represents part of a plane. So you can imagine this plane going on forever, but we're only drawing this part of it. What is the intersection of plane ADC, so that's this top plane here, and plane BFG, so that's this plane here. Where those 2 planes intersect? Now, we're two planes. We're not talking about just the two sides of this cube. We're talking about two planes. Two planes go on infinitely. So these aren't, we're not going to say that these intersect on segment BC, because planes go on forever and planes intersect on a line. So we're going to say they intersect on line BC. Ooh, pause the video and try this. So A, what are the names of two planes that intersect in line BF? Well, here's line BF. Looks like we got this plane here and this plane here. Well, so we just need to name those planes. So we can say plane BFG and plane AEF. How about that? Why do you only need to find two common points to name the intersection of two distinct planes? Well, think about this. What if I named this first plane, let's call it BFG, and the second plane we can call it BFE, can't we? We could call this plane BFE. And as long as G and F aren't both on this plane, basically as long as E is not on plane BFG, you know that these two planes intersect on line BF, because they both have BF on them, and through any 2 points there's exactly one line. So that means that that one line is in both planes. All right. So through any, here's postulate 1-4. Through any 3 non-collinear points, there's exactly one plane. So as long as R, S, and Q aren't standing in a line, there's only one plane that goes through them. All right, so what plane contains the points N, P, and Q? So N, P, and Q is like the bottom of this box, right about there. What plane contains points J, M, and Q? Here's J, M, and Q. So that's going to be a tilted plane that comes through here, and we can draw that like this. All right, see if we can pause the video and try this. All right, so L, we want a plane that goes through L, M, and N. So I'm going to draw a little bit of this and a little bit of this. It's also going to go through P, isn't it? And now I just need to shade that area. And it kind of looks like there's that plane cutting through that box. So reasoning, what is the name of a line that is coplanar with JK and KL? So if you imagine, if we got any 3 points, J, K, and L, we got a line JK and we got a line KL. What is a line that's coplanar with them? Line JK would be coplanar with them, because these 3 points make one specific plane. So line JL. Line JL is coplanar with those 2 lines. Okay, you made it. You made it to the end. Congratulations. Make sure you get notes. You can use your notes on the test. Go ahead and do practice 1, 2, and then work on your formal write-up. And I will talk to you later. Ta-ta.